In order to better understand why Final Fantasy was put together the way that it was, it's best to learn a little about the machine that it ran on. The story has been told over and over, but here's a quick rehash. The first PlayStation came about due to a falling out between Sony and Nintendo. Originally, the PlayStation was supposed to be a CD-ROM add-on to the SNES using Sony's new miniaturized controller technology. Nintendo, being the developer control freaks that they were at the time, wanted exclusive control on who made the games for the add-on. Sony wanted to have a cut because their technology became the gatekeeper. As that little argument was being hashed out by the lawyers, Nintendo snuck away and started chatting up Sony's competitors. When Sony caught wind of this, they withdrew from the PlayStation project, taking their shiny new CD technology with them. Nintendo, being the actual loser of the deal, proclaimed, "Oh yeah, well, we didn't need your silly drive anyway. We'll just make it cartridge-based, with blackjack, and hookers." Well, not so much hookers because of that whole control freak thing, but, you know. So now Sony had the CD-ROM designed for consoles and didn't know what to do with it. Then they realized they could just plug it into one of their System 11 arcade boards they were developing for Namco, and that's how the PlayStation was born. Now, normally to understand the architecture of the system, we'd be doing a teardown from the outside in. However, because the PlayStation is a little more strange on the inside as opposed to a typical PC, it'd be easier to virtually build the console so you can see the individual parts from the inside out. We'll start with the CPU. The PS1 uses an R3051 MIPS processor that was developed by LSI and customized by Sony. There's nothing really interesting about it to write home about. It's a simple R3008 compatible that runs just shy of 34 MHz. It also has all the weird nuances of being a MIPS chip. For example, the stack pointer being more of a suggestion than anything. The reduced instruction set in this particular computer completely did away with stack management commands such as push and pop. The CPU has an obscene amount of 32-bit registers, and function calls were designed to pass by value as opposed to passing by reference using a first in last out stack. But wait, you ask, what if I need to make a call on a call or want to pass a huge amount of data by reference? Well, we don't really talk about that at parties, and oh look, there's a stack pointer, you can use that, or really any other general purpose register really. What makes the CPU stand out though isn't so much its power or programming nuances, but the fact you can buy one for about $5, or if you get it in bulk under 10 cents each. Now, what makes the 3051 different than all the other chips in the R3000 series is how the coprocessors are configured. The CPU has support for 4 of them, named COP0, COP1, COP2, and COP3. COP0 is the memory manager, which is utterly crippled in the PlayStation. On a full-blown MIPS computer with gobs and gobs of memory, COP0 assigns different parts of RAM particular functions. Up here we have the protected operating system area, down here we have the user space area for programs, and then these little bits in the middle for hardware access and data caches. A data cache, in case you're wondering, is a bit of memory that when you access over and over again becomes faster, until you write to another part of memory to which then the cache is overwritten. Then things become slow again until you access that bit over and over again and you'll get your speed back. But the PlayStation didn't have 4 GB of memory, only 2 meg, so Sony made a few changes to how memory was managed. First, they decided to drop the protected memory area, as security was handled through developer licensing, and secondly, wire all the segments together so they all pointed to the same physical memory directly. Now, depending on which address the programmer used, he could use the cache or access the memory directly, saving the cache for something more important. Also, because the PS1 didn't have a hard drive or any type of writable media, save for the archaically tiny and slow memory cards, the virtual memory system was completely removed. COP1 was for floating point math coprocessors. Sony opted not to put one in the PlayStation 1. You would think they would though, with all the math needed to drive 3D worlds and the like. The problem is that floating point math is super awesome for doing highly accurate long-term statistical analysis, but is really a big pile of fail when it comes to video games. Games need numbers fast, and often use numbers that are good enough for the sake of time. You don't need that extra decimal precision, especially when the end result's going to be shown up on a screen for 1/60th of a second. The CPU, however, can only do simple integer math, with no concept of a decimal point out of the box. That wasn't going to cut it either if they're going to make a 3D video game system. So Sony developed a special coprocessor called the Geometry Transformation Engine, or GTE, and placed that at COP2. This was a special math chip that did slightly less accurate fixed-point math and came preloaded with a whole bunch of slick hard-coded 3D functions, like moving a 3D object in space and calculating how it can draw 3D polygons in a 2D screen. It also had some functions for calculating lighting as well. They didn't put it where the old math coprocessor used to be because the GTE did math that was way out of spec of what MIPS was expecting. It was better to just let any third-party programming tools know that the standard math coprocessor was simply unimplemented. COP3, which is a spare slot, was left empty. The CPU sits on a data bus that connects everything to everything else on the system. The graphics processor, called the GPU, is also connected to it, and this is where we run into another one of the PS1's oddities. On a typical computer system, the video RAM, or VRAM, hangs out with the regular memory. Its only difference is that it's faster, and when you write to it, the data goes to the frame buffer, which shows up on the TV screen. This is why you hear some people say that the PS1 has 3 megabytes of memory. Technically, it has 4, including the CD-ROM and audio buffer, which both weigh in at 512K each. Functionally, however, it only has 2 megabytes of accessible RAM, and the VRAM is locked behind the GPU. The CPU has no direct access to VRAM and cannot store arbitrary data or run programs from there. Now that begs the question, if the VRAM is inaccessible, how does the CPU draw things on the screen? And the answer is that it doesn't. The GPU does. It only accepts commands given to it, such as setting the resolution, getting palettes, and drawing things like dots, lines, triangles, quadrilaterals, and sprites. No circles though, because of that whole decimal thing. Unfortunately, having the CPU stop and feed the GPU graphics commands is a colossal waste of time, especially when it needs to be doing something a little bit more important like running the game. To help things along, a direct memory access controller was added so that the GPU and other chips can move data to and from RAM without the CPU at all. The 1 megabyte of video memory gives the GPU an effective drawing surface of 1024 by 512 pixels with 16-bit color, or 960 by 512 by 24-bit color if you want to have more colors on the screen at the cost of frame buffer size. Now the PS1 couldn't display all these at once. The most resolution you could have was 640 by 480. Remember though that the system was originally designed for low resolution analog TV sets. Most of the time, games configure the frame buffer with two 320 by 240 by 16-bit views for page flipping, or optionally 24-bit at the cost of being more video memory again. A neat note about the color management is that the PS1 could actually hold and display different color depths at the same time. Almost always there was a little spot down here that was used for holding color lookup tables for 4 and 8-bit graphics, along with the 16 and 24-bit direct color modes. The texture area over here stored the bitmaps that were used to texture polygons and sprites and such. This area was cached, decreasing in speed until you got to the end where you mostly kept your static 2D graphics. A big drawback to textures being drawn in 3D polygons is that the GPU didn't know that they were 3D. The GTE did all the 3D math and projection before it was handed off to the graphics chip. With the depth data gone, the GPU had no way of interpolating the texture away from the camera. This meant that the PS1 could only do what was called a fine texture mapping, which made all the textures look skewed when it was rotated on the Z-axis. Lastly, as the GPU dragged the electron beam across the TV screen to make a picture, it would broadcast when it finished every pixel, every line, and every frame. These were called root counters, and you could attach events to them to make something happen when they were fired. Leaving the land of video processing, we next step to the audio. This was handled by the sound processing unit, also known as the SPU. This is actually a direct descendant from the SNES's SPC700 based sound processor. This chip carried with it a 512K sound buffer for storing and playing back samples. It also had the ability to play 24 sound channels at the same time, each with its own attack, sustain, decay, and release envelopes. It also had a global reverb mixer as well. Some of the buffer was reserved for CD audio, coming directly from that controller. The CD controller itself was able to take commands from the CPU, much like how the GPU could take commands for drawing. You could issue CD audio requests such as play, pause, stop, and track up or track down. You could also tell it to directly read a data sector or check the region code and copy protection on the fly. Speed-wise, the CD-ROM itself only ran at 2 times speed though, but it had a 512K buffer for speeding things up somewhat. The PS1 also supported another chip called the motion decoder, or MDEC. Unlike its name, it was really limited to only decoding single compressed 16 by 16 pixel blocks that were encoded using a JPEG-like format. It was super fast though, so you can stream these blocks and stitch them together to make an image. If you wanted to make a video, you could overwrite each picture with another picture. The chip didn't process any audio though, so streams are often interleaved with both video and audio, and the audio was split to the SPU's sound buffer. Anything more advanced than that, such as keyframing, was something the MDEC couldn't do at all. Now, since the console was derived from an arcade machine, the PlayStation was supposed to have 4 universal ports on the front for both controller and memory cards. Electrically, the ports are all exactly the same. However, there were issues that couldn't be resolved about how the ports were supposed to be assigned. It was then hard-coded in software that ports 1 and 2 were the controller ports, and ports 3 and 4 were going to be the memory cards. They changed the shape of the external ports, keeping the 9 pins exactly the same so you couldn't accidentally plug in the wrong thing in the wrong slot. Finally, snuggled next to the 2 megabytes of RAM is the popular PlayStation BIOS. This holds a 512K program that provides the basic input-output system. When you first power up the PS1, it's the program that comes up on the screen. It also holds the memory card and CD player utilities. Behind the scenes, all games written for the PS1 must go through the BIOS to access the hardware. This is why PS1 games seem to be compatible with everything that Sony makes. It provides a translation layer for massively different systems. It's also why the BIOS is so critical to emulation. The games don't know where the hardware is, they just know what the BIOS does. The BIOS also has a tiny 64K OS. This is used to load the initial game executable, offer event handling facilities, hardware API, and some libc functions. And this, in a nutshell, is the entire PlayStation system. So the question is now, how do you program this mess? You did it with a special game programming library called Psy-Q. Gesundheit. Psy-Q, you're welcome, is a game programming library that was created by Psygnosis, and if the logo didn't look enough like a heavy metal rock band from 1978, you should have seen what the box art looked like for their video games back then. Besides the programming software that came with the kit, there are two major pieces of equipment that came with it too. The first was a sound card that you plugged into a Mac. This had its own Sony SPU in it so that when you designed your sound and music, it sounded exactly the same as it did on a real PlayStation. The second card that came with the system allowed a PS1 to use the PC's hard drive as opposed to the CD-ROM for development. This means you didn't have to burn a new disc every time you wanted to test your game. Finally, there were tools to convert PC-friendly audio, graphics, and 3D files to something a little bit more native to the PS1. This was so Psy-Q could feed the data a little bit more directly to the hardware. When Final Fantasy was ported to the PC, they weren't allowed to use Psy-Q or any of its file formats. To get around this, they made a monolithic Psy-Q-like driver and used the original non-converted versions of the data files, or they converted it into something else that could be loaded by their custom code. This Psy-Q driver code is actually still in active development by both Square Enix and a fan community, each with their own ends. The Square Enix version is hooked into Steam and can be used for achievements and cloud saving. The fan version, however, is designed to accept and use mods that were created by the community. And that, in a nutshell, is an end-to-end crash course on the PlayStation and just a light touch on the development for it. In our next episode, we'll be jumping back into Final Fantasy VII and examining the boot process and taking a look at how the kernel sets the framework for the rest of the game. I hope to see you there, and thanks for watching!